Imagine a universe where matter and antimatter collide, unleashing energy with the brilliance of 1,000 suns. This isn't science fiction, it's the tantalizing reality of antimatter, a counterpart to the everyday matter forming everything from stars to the human body. Antimatter sounds like a concept straight out of a cosmic thriller, which holds keys to revolutionizing our understanding of the universe. Antimatter is the mirror image of matter, possessing opposite charges but identical mass. Its interactions promise not just scientific breakthroughs, but also practical applications that could transform energy production, medical technology, and space travel. The journey through the enigmatic world of antimatter not only challenges our fundamental understanding of physics, but also invites us to rethink the boundaries of what is possible. By delving into the nature and potential of antimatter, we open a portal to the most extreme conditions of the cosmos right here on Earth. As we explore this extraordinary field, we encounter the building blocks of our universe in their most bizarre forms and begin to unlock the cosmic powerhouse that antimatter represents. Every particle in the universe has an antimatter counterpart, known as an antiparticle, which has the same mass but opposite charge. For instance, the antiparticle of an electron is the positron, which carries a positive charge. This symmetry is not just a curiosity, it's a fundamental aspect of how our universe operates, suggesting a deep connection between matter and antimatter. When a particle meets its antiparticle, they annihilate each other, releasing energy in the process. This annihilation is not merely a destructive event, it is a transformation of mass back into pure energy, as described by Einstein's famous equation, E=mc2. This equation implies that a tiny amount of matter and antimatter can produce a tremendous amount of energy, far surpassing conventional energy sources. This incredible energy potential makes antimatter a highly attractive subject for research. The ability to control and harness this power could lead to energy solutions that are currently unimaginable, providing clean, nearly limitless power. The challenges are immense, but the potential is even greater, promising a revolution in how we generate and use energy. Antimatter is naturally produced in some radioactive decays and cosmic ray interactions, which occur throughout the universe. On Earth, scientists create antimatter in particle accelerators, colliding particles at high speeds to produce antiparticles. These facilities are not just laboratories, but gateways to understanding fundamental physics, replicating and studying conditions that existed just after the Big Bang. Detecting antimatter requires sophisticated technology. Instruments like the antiproton decelerator at CERN or the alpha magnetic spectrometer on the International Space Station are designed to identify and study antiparticles. These detectors help scientists understand how antimatter behaves and how it can be manipulated, which is crucial for any practical application. The creation and detection of antimatter are not only about pushing technological limits, but also about understanding the laws of nature. Every experiment brings us closer to harnessing the potential of antimatter, whether it's powering spacecraft or transforming our approach to energy production on Earth. These endeavors underscore the innovative spirit of scientific inquiry, driving us toward a future where the impossible becomes possible. Section 4. The promise of antimatter, energy, and space travel. The potential of antimatter as an energy source is staggering. Just a few grams could provide the same amount of energy as millions of gallons of conventional rocket fuel. This immense energy density makes antimatter an ideal candidate for future space propulsion technologies, potentially reducing travel time to distant planets and stars from years to months. In the realm of space travel, antimatter could fuel interstellar journeys, making the dream of traveling to other star systems a more tangible reality. Current propulsion technologies are limited by the energy they can carry and use efficiently, but antimatter offers a solution that could leapfrog these limitations, opening up the cosmos for human exploration. Moreover, the use of antimatter in space travel would revolutionize our approach to exploring and understanding the universe. With faster travel times and more efficient energy use, antimatter could enable missions that are currently beyond our technological reach, including sending human missions to explore exoplanets or even other galaxies. Section 5, Antimatter in Medicine, a frontier for health technology. Antimatter has found a surprising application in the field of medical technology, particularly in the diagnosis and treatment of cancer. Positron emission tomography, or PET scans, utilize positrons, the antimatter counterpart of electrons, to detect changes in body tissues, offering a powerful tool for early detection of diseases. In these scans, a small amount of radioactive material that emits positrons is introduced into the body. When these positrons encounter electrons, they annihilate, releasing detectable gamma rays. This allows doctors to create detailed images of internal tissues, making PET scans an invaluable tool in the medical arsenal, providing insights that other imaging techniques cannot. Beyond imaging, research is ongoing into the direct use of antimatter in treating cancer. Targeted antimatter particles could potentially be used to destroy cancer cells with extreme precision, minimizing damage to surrounding healthy tissues. While this application is still in the experimental stage, it represents a frontier in medical technology, harnessing the power of antimatter for healing. Section 6, the cosmic puzzle. Why scientists focus on antimatter? Antimatter isn't just a tool for advanced applications, it's also a fundamental puzzle in our understanding of the universe. According to theories of the Big Bang, the birth of the universe should have created equal amounts of matter and antimatter. Yet today's universe is overwhelmingly made of matter. This asymmetry is one of the biggest unanswered questions in physics. Studying antimatter allows scientists to explore the conditions of the early universe, testing theories about how matter came to dominate. It also provides a unique window into the behavior of fundamental forces under extreme conditions, contributing to our understanding of the fundamental fabric of reality. This focus on antimatter is more than academic curiosity. It's about understanding the very building blocks of our existence and potentially discovering new physics that could lead to unforeseen technological advances. The mysteries of antimatter challenge our current knowledge and push the boundaries of what we know about the cosmos. Section 7. Conclusion. A glimpse into the future. Antimatter, with its immense potential and profound mysteries, stands at the frontier of modern physics and technology. Its study not only challenges our understanding of the physical laws that govern the universe, but also offers a peek into the vast possibilities of future technologies. From energy production to space travel and medical technology, the applications of antimatter are as vast as they are impactful. As we continue to explore and harness the powers of antimatter, we are not just solving scientific puzzles, we are also paving the way for a future where the limits of energy, health, and cosmic exploration are redefined. The journey into the heart of antimatter is not merely about scientific discovery, it's about unlocking new realms of human potential and taking our first steps into a broader universe. By embracing the mysteries and challenges of antimatter, we keep the doors open to an exciting future, driven by curiosity and powered by an almost limitless energy. The story of antimatter is just beginning, and its chapters will be written by the daring and the bold who dare to dream of the impossible made possible.